Hello everyone, today we're going to go over the blind 75 in C++, and today we're working with binary tree maximum path sum. Now, before we get started, feel free to pause the video in order for us to be able to go over the questions if you're following along. To break down our question, we always ask ourselves these 4 questions. What are inputs going to be? What data structure / algorithm / technique to use? What to do with the data? And finally, what are outputs going to be? So, to give a breakdown of the problem, a path in a binary tree is a sequence of nodes where each pair of adjacent nodes in the sequence has an edge connecting them. A node can only appear in the sequence at most once. Note that the path does not need to pass through the root. The path sum of a path is the sum of the nodes' values in the path. Given the root of the binary tree, return the maximum path sum of any non-empty path. Okay, well, it looks like from the following over what we need to do is that we need to find the path sum accordingly just based within the binary tree, and even looking at more of the examples, it looks like from the following path we have to sum up all the given values and return a maximum sum. So at first we're given the root of a binary tree, then we need to return the maximum path sum of the non-empty path, which means that there needs to be children on either option of sides where there is no null. And the technique in order to help us solve for the following problem, trees two optimal solutions to be able to actually solve this type of problem. 2 types are depth first search or breadth first search, and depth first search is widely used for connectivity while breadth first search focuses on the level. And for this problem we're going to use depth first search with recursion by creating our depth first search function to call upon within our main function and return the max sum. So steps for us to be able to accomplish this are the following. Step 1, we're going to initialize the max sum to be the int min. And for step 2, what we're going to do is that we are going to call on our depth first search helper function, which will be called DFS, incorporating the root, and then the max sum, which are going to be your 2 parameters to add, and then this will be later down. We are going to return our max sum. In fact, I'll just make it part 3. This will be inside of our main function. And then inside of our depth first search recursion function, what we are going to do is that 1, we will initialize our we will take care of the edge case. If a node is null, we return 0. That's the first step. Then for each node on both the left and right children in the tree, we are going to calculate the max path. Then what we will do is that we'll calculate the current node's max value considering the node itself, the node plus left child, the node plus right child, and the node plus both children. And then what we will do is that we will update the max path sum with the current max value, and finally we will return the max path sum of the current node to its parent. Alright, so now let's just be able to go through what we need to do. So inside of our main function, this is how it's going to look like in these 3 steps. So step 1, step 2, step 3, and then for a private function, search function. We're going to have private int DFS for a tree node, similar in the case for the root. We just copy this parameter over here, and then we're going to have our max sum, which is going to look like this: int and max sum. There we go. Or following. There we go. All right, and we will set up the steps. Step 1, step 2, step 3, step 4, step 5. Okay, so for the max path, the way how it's all going to be set in place for the first part, we initialize our int max sum, int max, int min as a given value that we need. And then for step 2, we're going to call upon our def for search function for the root and max sum. And for step 3, we're going to return our max sum. And then within our def for search function, what we will do is that we're going to have our no equal null pointer and return 0. Then for step 2, we will take care of both of our left and right children. So int left and then int right. We're going to equal that to the max path. We're going to be using recursion in this case, and just really getting the max path by using max for the node that is on the left, and then the max sum, we're just calling upon the def for search function and just getting every single node value that's on the left. And then we'll do the same for the right. One second. Stupid. Again, def for search is really good for directions. And then we're going to move forward. We're going to calculate the current node's max value considering the node itself. So that means it's going to be int sum is equal to node value plus the left plus the right and then what we will do, we're just basically doing this entire one. And then node for both children, that's right here. And then we're going to update our max sum, where it's going to be max sum, and finally what we will do is that we will return the max path sum of the current node to its parent. So the way it's going to look like, since we are returning to its parent, val plus the max of the left and right. So this is the way how it should look. Even though this is a hard problem, the solution is pretty self-explanatory. Already right over here, we're getting out the different directions between the left and right children. Let me just double check to see if we have everything right. All right. There's just a syntax error over here. I thought I declared node earlier. Oh wait, I forgot to make this a node. Yes. So it's not the root, it's technically the node that we have to make an agnostic. Apologies on that. So this is what it should look like. Okay, there we go. So we have a node that we are updating inside our def for search function. The parameters will be the node and max sum. Alright, now we submit. Okay, now just to give a breakdown on the space and time complexity for our following solution is that the time complexity for our solution is actually really efficient. It beats a lot of other solutions as well. The time complexity is going to be O of n, where n is the number of nodes in the binary tree, and this is because we traverse each node at least once. However, the space complexity is going to be O of h, where h is the height of the tree, and this space is used for the recursion stack and the depth for search, with the worst case scenario being a skewed tree resulting in O(n) space complexity. So yes, this was Sorry. This was binary tree maximum path sum. Thanks again for taking time to watch this. If you found this helpful, feel free to like and subscribe. And if you have any other questions, feel free to put them in the comment section. And as always, take care. Cheers. Bye-bye.